Hey, how you doing? Hoping you're having your great Thanksgiving weekend away from school, but I know you really wanted to get back into some algebra. So we're going to talk today about complex numbers, as if numbers weren't complex enough for you already. Radical expressions, which is really just square roots for us, and imaginary numbers, because, regular numbers weren't good enough. We need some make made up ones. So we're going to decide whether every complex number is an imaginary number or not. There's your work that you're going to take a look at on Monday. Square roots. You can take things and just split them up, is the basic idea of what these things are saying here. So if I have square root of 3 times 5, I could rewrite that as the square root of 3 times the square root of 5. It's useful. It may not seem like it right now, but it is. Same thing with my fractions here. You can split it up and just do the square root on the top and the bottom and deal with them separately and work with them that way. Simplifying a square root, there's lots of different ways to go about doing that. Main thing is you want to think about perfect squares that go into it. Perfect squares being things like 2 squared makes 4, 3 squared makes 9, 4 squared is 16, 5 squared 25, and so on. So you want to find these ones because, well, do I know what the square root of 25 is? Yeah. That might help me figure out a little bit of what square root of 72 is a little bit easier. So what goes into 72? 36 does. So instead of writing it as 72, we're going to write it as 36 times 2. Use that property we just talked about to split it into two different guys. Do I know what the square root of 36 is? Yeah, it's 6. So we got 6 square root of 2. And that's our simplified version. It makes things look a little bit easier and we can do some canceling and some stuff like that when we're inside of fractions. Another way is to take your 72 and break it down into all of its prime factors. The way you do that is you think, well, what multiplies to make a 72? 36 times 2 we just discussed. Here might be 6 times 6. What makes a 6? Well, a 3 and a 2 and a 3 and a 2. So you kind of take all those bottom numbers, and that's what we have written right up in here. 2 times 2 times 2 times 3 times 3. It's 3 2's and 2 3's. Isn't that funny? Well, any pair of those is a perfect square and thus makes it to the outside. So we've got a pair of 2's and a pair of 3's. 2 times 3 on the outside, then makes 6. Our lonely 2 here in the middle had no buddy, he didn't get out. So that's two different ways to go about these things. Square root of 8 here, I'm going to think about, hey, that's square root of 4 times the square root of 2. 2 times 4 makes 8. What's the square root of 4? 2. So we got 2 root 2. Square root of 175. Well, what multiplies to make that? Hopefully you look at that and think, hey, it's kind of like quarters, $1.75. So 25 times 7. Put those in our square roots. Square root of 25 is 5. So it's 5 square root of 7. Now, when you look at something like this, to me, this one's not as easy to see a nice perfect square in. So we might want to do the breakdown method here and find our prime factors. Well, I know 2 goes into it because it ends in 8. It's even number. 2 times 54. Well, what multiplies to make a 54? Well, I'm going to just cut it in half again and get 2 times, what's that, 27? Well, what makes a 27? 9 times 3, and 9 is a 3 times 3. So we've got a whole bunch of numbers down here on the bottom, and 2 of them happen to be pairs. So we've got 2 times 2 times 3 times 3 times 3. 2 of them are pairs, so they're going to get on the outside. This lonely 3 here, he didn't have a friend, he stays on the inside. 2 times 3 out front gives me 6 square root of 3. So that's another way to go about doing it. It doesn't matter which way you go. You might realize, hey, 36 goes into 108 3 times. If that's the case, you're an amazing human being. Let's go ahead and give example 4 a try on your own. Hit pause, take a look at it, and see how things go for you. Next, we're going to look at rationalizing a denominator. And that's just kind of fancy math talk for get the square root out of the bottom of the fraction. We don't like it down there. It's hard to divide by square roots. And way back in the day, people used to use these things called slide rules. This is before calculators, so your parents probably don't even know what they are necessarily, but my parents, since they're super old, My dad actually used one of these back in high school at Rancho, where he went. So they had to slide these things around, and you couldn't do a slide rule problem with a square root on the bottom. You could deal with it on the top, but on the bottom, all of this wasn't working. So they had to go through some math to make sure it got out of there. This is based on the fact that something over itself is going to equal 1. Kind of like how 5 over 5, well, what does that equal? It equals 1. So even if it's crazy, like the square root of 8 over the square root of 8, it still equals 1. So we're going to multiply by 1. We're just going to make the 1 look like this. Multiplying by 1 doesn't do anything but change the way things look. So square root of 8 over square root of 8, 3 times 8 on our top is where we get the 24 here. Square root of 8 times square root of 8, well, that's the square root of 8 times 8, which is the square root of 64, which is back to 8. So the whole reason we do this is now we don't have a square root on the bottom. We've taken care of it and just gotten the 8 down there. But of course we're not done, because we can simplify this square root. That 24 has got to go. 24 is 4 times 6. We know the square root of 4 is 2. And 2 times 2 makes a 4 on the outside. And no, folks, we're still not done, because it's fractions, and we know how much you love some fractions. So 4 over 8, let's reduce that to 1/2. And there's that imaginary 1 in front if you want to put it there, think about it. So 4 over 8 just reduces to 1 over 2 with our square root of 6 on the top. Alright, so what are we going to multiply here by? But square root of 3 over the square root of 3. What's that going to leave us on top? Well, 2 root 3, there's nothing to do. We just put them there. That's pretty easy. Square root of 3 times square root of 3 is square root of 9, which goes back to 3. Exactly why we did it. The roots cancel out. We're left with just 3 on the bottom. Do not be the kid that tries to do this right here and cancel these out. No, that kid makes me so sad. You're going to want to do it because you want to make it simple and say that equals 2, but no, it doesn't equal 2. Square root of 3 over 3 does not just cancel out and go away. So this, as ugly as it may be, is our final answer. Oh, fancy. So go ahead and give example 6 a try on your own. We'll probably take a look at it in class and make sure you did things correctly, but see if you can rationalize that denominator. Alright, this leads us to something I know you're going to be excited about, the imaginary number I. Because regular numbers just weren't good enough. We had to go and figure out, hey, how can we make things crazy? Let's just make up a number, right? Well, I goes back a long, long ways. Trying to figure out the square root of something, and you end up with the square root of a negative number, just doesn't work. You don't know what to do. So the first guy that actually wrote it down and something that people found was this guy Heron of Alexandria. Lived in Alexandria in Egypt. In about 50 AD, he wrote this book, and he is working out a problem trying to find the volume of some kind of pyramid, and he got the square root of 81 minus 114. And it just kind of made him angry, because number one, back then they didn't even have negative numbers. So number two, this is just a mess to him. He got frustrated, it just didn't make sense. So he did what most of you guys would do. He just kind of walked away and quit. Said, I don't want to deal with it. So for like 1,500 years, nobody really dealt with negative numbers inside of a square root. Till this guy, I'm not even going to try and say his name, but he wrote this book called Ars Magna in 1545, and he was working out some stuff, and he got answers that looked like this, where you got 5 plus or minus the square root of a negative number. He didn't like it. He put it in his book, but he really, really hated it. He kind of thought that they were useless, they didn't help you get anywhere, and he actually called them mental torture, which is probably a term you guys are going to feel in the next few days going through these things, a little bit of mental torture. But he hated it. So then it comes to this guy in 1637, Rene Descartes, came up with the XY coordinate system that you guys are using in algebra class all the time. He did a lot of things, really pushed math forward, and he hated the imaginary idea too, the square root of a negative number. He didn't like it. He actually called it imaginary, and it still goes back to him because of that. But he was calling it to make fun of it, kind of like how you have the big guy friend and you call him tiny. He was making fun of the numbers being imaginary and people that used them. Because who would do imaginary math? That's just ridiculous. So he used imaginary kind of in an ironic way to make fun of it. But as things go, his satire stuck and it kind of stayed with it. So then it comes to this guy, Leonard Euler, or Euler, I think is probably how it's supposed to be pronounced. Had a lot of stuff that's kind of named after him. A lot of things in geometry class you might remember with this guy's name on it. Have to do with the vertices and the sides of your three-dimensional shapes. Well, in 1777, he was the first one to call it I, and that was a nod to Descartes and the fact that he made fun of it, calling it imaginary. And so he's the first one that wrote it down and called it I and said I equals the square root of -1. And this is going to allow us to deal with all of these things that we need to get through. That led us to eventually this guy named Carl Friedrich Gauss. He did a ton of stuff. He's probably one of the more important modern mathematicians of all time here. 1831, he finally kind of started writing some stuff down using I and made it okay for other people to use it. So, even though its origins go back to, 50 AD, it wasn't until about, 1831, so it's just a couple hundred years ago almost, that people actually started using it on a regular basis and accepting it as regular math. Today, engineers use it in all kinds of stuff. It has a lot of things to do with water flow, apparently, that I don't know about. Electric circuits, things that people have done with those are need I in order to solve problems with that, and radio wave transmissions. So the computer or the cell phone that you are watching this video on right now would not have been created were it not for people using the imaginary number I in order to get there. So what is it? Well, square root of -4. What is that? Well, we know the square root of regular 4 is 2, because 2 squared gives you 4. That's 2 times 2. Well, what number times itself is going to give you a negative number? It can't happen, because -2 times -2 also gives us that +4. So it's just not going to work. There's nothing there. That's why we had to come up and call it imaginary. So how we use it is actually pretty easy. Square root of -4. We just think about, well, it's the square root of -1 times the square root of 4. Square root of -1 goes back to I, so we just write I. Square root of 4 is 2. So we write 2I, and we walk away and think, hey, that's awesome. That's it, 2I. We kind of stick it in the backside of numbers just like we do with x or any other variable. So here, square root of 64. We just think, what's the square root of 64? Well, that's 8. Is it negative? Yeah. So put an I on it. Square root of 64 is just 8I. Alright, square root of 168. Ugh, I don't know what that one is. Well, it's got the negative here, so I know an I is going to come out. But what things multiply to make 168? I'm going to break it down the slow way here. 2 times what? Well, that's 1/3. 84. There we go. What makes an 84? I don't know. 2 times 42. 2 times 21. 3 times 7. Alright, so I got 2 times 2 times 2 times 3 times 7. What kind of pairs we got? That's it. So a 2 is going to come out on the outside. That negative means I'm going to put an I there. And these guys don't have friends, so they're stuck on the inside. 2 times 3 is 6. Times 7 is going to leave us with 42 on the inside here. So 2I root 42 is our ugly looking simplified answer here. Alright, so go ahead and take a look at example number 10. Give it a try, and we'll see you back in class on Monday.